Welcome to our electronics series where we explain the working of each component.
Hey everyone, welcome to this explainer. Today, we're tackling a classic engineering problem, taking a 12-volt DC input and efficiently stepping it down to a highly stable 5 volts using a buck converter. If you've ever wondered how your high-powered batteries can safely run delicate 5-volt microchips without just burning off all that excess energy as heat, well, you're in exactly the right place. We're going to deconstruct exactly how this works.
Here is our roadmap for today. We'll start with the buck converter system itself, dive into the core circuit components, break down interval T1 when the MOSFET is on, interval T2 when it's off, and wrap up with output and efficiency. Let's get right into it.
Section 1. The buck converter. Let's start with the big picture system overview.
Okay, tracing the path of power here, we're starting from the 12-volt battery on the far left, flowing through a series of specialized components and ending up at the output load on the right. That is exactly where we want our smooth 5 volts to land. This entire setup is brilliantly designed to step down the voltage without losing a massive amount of power in the process.
Moving on to Section 2, Core Circuit Components. Let's see what's actually building this circuit.
So what are our exact building blocks? We've got our 12-volt DC input source, of course, but pay special attention to the IRF 740 MOSFET. Now, this isn't your standard mechanical wall switch. It is an ultra-high-speed electronic switch. We've also got a UF 4001 diode stepping in to provide a freewheeling alternative path, a 330 microhenry inductor for energy storage, a 220 microfarad capacitor acting as a voltage filter, and finally a 5 ohm resistor sitting there as our target output load. But how on earth do we control that high-speed MOSFET? Well, the secret sauce here is PWM, or pulse width modulation. Basically, this is an invisible electrical signal applied right to the MOSFET gate. It controls exactly how long the switch stays on and off by changing what's called its duty cycle. Think of it like a hyperactive toddler just rapidly flipping a light switch on and off to dim a room. That's essentially what PWM does to control our power.
The absolute coolest part is that once this circuit actually goes live, every single component has a highly dynamic role to play. The MOSFET is firing on and off literally thousands of times a second. Meanwhile, the inductor is actively storing energy in its magnetic field. The diode, it's just standing by, ready to provide an ultimate path for the current the second it's needed. And right at the end of the line, the capacitor is smoothing out the voltage to reduce any harsh ripples. It's an incredible, synchronized team.
Section 3. Interval T1, MOSFET on. Let's look at the charging phase.
Picture the current flowing in a totally direct path during this T1 interval. It surges out of the 12-volt battery, shoots straight through that newly closed MOSFET switch, travels through the inductor, and finally reaches both the capacitor and the load. This is the primary charging phase, where raw power is actively pumping into the system from our main source.
But it's not just passively traveling, it's doing heavy lifting along the way. This is the energy storage phase. As the current pushes through the inductor acts almost like a sponge, soaking up energy and storing it as an expanding magnetic field. Now, during this exact split second, absolutely zero current flows through the diode. It's reverse biased, so it essentially acts like a locked door. All the action right now is purely focused on building that magnetic field and pushing direct power to the load.
All right, Section 4, Interval T2, MOSFET off. Time for the discharge phase.
Now, you might intuitively think, okay, the switch opens, power to the load stops instantly, right? Well, no way. And that's all thanks to the fundamental property of inductance. You see, an inductor inherently resists any sudden changes in current. All that energy it just aggressively stored up during T1, it's got to go somewhere. It cannot just magically vanish. This physical resistance to change is literally the foundational principle that makes this entire converter function.
Because of that stored energy, trying desperately to keep the current flowing, a completely new current loop is forced into existence. The current now starts circulating from the newly forward-biased freewheeling diode, which, by the way, has now unlocked its doors to allow flow through the inductor, into the capacitor, and onward to the load. So get this, even though the main battery is completely cut off, the load is still getting power fed entirely by the collapsing magnetic field of the inductor.
It's a pretty brilliant duality when you break it down. During T1, the MOSFET is on, the battery is connected, the inductor stores energy, and the diode is reverse biased. Then bam! During T2, the MOSFET is off, the battery is totally disconnected, the inductor releases that stored energy, and the diode is forward biased to complete the loop. They work in perfect tandem to give the load continuous power.
And that is exactly why this converter is so ridiculously efficient instead of just burning off all that excess voltage.
Finally, Section 5, Output and Efficiency. Let's talk about stable DC voltage. The capacitor continuously smooths the output voltage by reducing switching ripple. What does that actually mean for us? Well, without this crucial little component, our sensitive electronics would just get battered by a violent, rapidly switching wave of power spikes. But the capacitor essentially acts like an electronic shock absorber. It eats those harsh pulses, fills in the valleys, and filters the whole messy thing into a nice, stable, flat DC voltage that our electronics can actually use.
And that brings us to the ultimate mathematical payoff for the whole system. The output voltage simply equals the duty cycle multiplied by the input voltage. This is huge. It means by simply tweaking the duty cycle of our PWM signal, basically just changing the percentage of time the MOSFET is turned on versus off, we can precisely dictate our final output voltage. It is simple, it's elegant, and it's 100% controllable.
And here is our final result, a clean 5 volts. Through rapid switching, smart energy storage, and precise filtering, we've successfully taken our 12-volt input and stepped it down to a perfectly smooth, stable 5 volts.
Now, understanding this matters immensely, because we're not just playing with an abstract simulation here. This highly efficient method of DC voltage regulation is literally the backbone of modern electronics. We're talking computer power supplies, basically all of your daily battery-operated gadgets, the drivetrains in electric vehicles, advanced robotics, tiny embedded systems, you name it. They all rely heavily on buck converters to give their processors and motors exactly the power they need, without wasting precious battery life as heat.
So I'm going to leave you with this thought to ponder. As our electronic devices get increasingly compact and vastly more power-hungry, how might the next evolution in MOSFETs and inductor materials push the boundaries of buck converter efficiency even further? As our reliance on battery-powered tech just explodes day by day, how will advancements in these core components redefine energy efficiency tomorrow? It is a massive frontier for engineering.
For more videos like these, follow our channel.